Hello, good evening.
Good day, sir.
Yeah, is my video visible? Hello,
Sir,
my
practicing presentation.
my video is not visible.
No, only
Okay, yeah, please stay online. I will just disconnect and call. Um, yeah,
yes, sir. Now visible.
yeah. So good evening and welcome to today's live interaction session. So my session used to take place generally on Tuesdays between 7 and 9 p.m. And there was a clash, there was overlapping of time with the other live interaction session. So I decided to, move it to Saturday's evening so that we can ensure better participation and whatever doubts are there, we'll try to resolve in today's session and we'll take up the sample questions as usual. So I will turn off the camera and I'll start today's session. Yeah, so if there is any doubt, again, feel free to unmute yourself and we can discuss those doubts as we
Sure,
proceed.
sir. Sure. Thank you.
Yeah, yeah. So I hope you have watched week six of the lectures already. Yeah, so I hope that my screen is visible now.
Sir, yes, sir.
Okay, okay. So again, I will give a formal introduction. So welcome to the week six of the live interaction session of the course Advanced Reinforced Concrete Design. This course is brought to you by NPTEL and course instructor is Professor Surya Prakash from IIT Hyderabad. And presently we are in the week six of the live interaction session. So in the earlier sessions, we have looked into various aspects such as the uh, brief overview of the reinforced concrete systems, then the material properties, then the various durability issues, and then we looked into the behavior of reinforced concrete members under axial loading. And presently, in weeks 5 and 6, we are studying the behavior of the reinforced concrete members under flexural loading. And this session is brought to you by me. My name is S. Dalit Savir. I'm a doctoral candidate and PMRF fellow in the Department of Civil Engineering at IIT Delhi. So I welcome you all to the live session. And just I'm going to brief about the today's agenda for today's session. So we are dealing with uh, module 5, continuation of the previous uh, week's contents that is concerned to the behavior and design of reinforced concrete members under flexure. So in module 5.3, we are going to be studying, we are going to be solving the sample problems on the effect of axial compression on the moment curvature analysis of the reinforced concrete members. So we are going to derive the moment curvature curves for the reinforced concrete sections under bending with axial compression. So in modules 5.1 and 5.2, we considered a singly reinforced beam and we did not consider the effect of the axial compression. So in module 5.3, we are considering the axial compression and what will be the implications of the axial compression. What will be the implications of the axial compression on the moment curvature plot of the reinforced concrete beam. So we are going to subject the RCB to different ratios of axial compression. That is zero point 0.1, uh, that is 10% of the axial capacity, 20% of the axial capacity. Then we are going to plot the moment curvature plots. Then we are going to compare what would be the influence of the axial compression on the moment curvature behavior. So what do we mean by the moment curvature behavior is that we are going to evaluate the gain in strength and the gain in the deformability. So the gain in strength is represented by the moment capacity. Gain in the deformability is evaluated through the curvature, through the ultimate curvature. So that is the essence of module 5.3. And in module 5.4, we are going to consider the doubly reinforced cross section. So in a singly reinforced cross section, we are going to provide the reinforcing steel only in the tension zone. However, to improve the moment capacity, we are going to provide the reinforcing steel in the tension zone as well as the compression zone. So we are going to evaluate the moment curvature plots for the doubly reinforced cross sections. So this will be the broad uh, outcomes of today's session. That is, we'll be able to draw the moment curvature curve for RC sections with the compression reinforcement. Then we're going to be able to discuss the effect of the compression reinforcement. So what will be the influence of the different compression ratios on the overall moment curvature behavior? And then we also saw what are some of the reasons for providing the compression reinforcement. And then we are going to establish the relation between the moment curvature and the load deflection. Okay. So with that, I think we can start the sample problems for today's session. So here is one numerical. So we are going to be solving numerical problems and also some conceptual problems, theoretical conceptual problems as we proceed. So first, we are going to consider a singly reinforced beam. So we are going to take it as the reference point, and then we are going to use this data as the reference for other advanced problems such as the beam under axial compression and the beam with compressive reinforcements. Okay. So I request you to kindly read the problem and then start solving the problem in order to obtain the ultimate moment capacity and the ultimate curvature. So the geometric properties and the material properties are given. So I'm going to start solving the problem with you. So if there is any concern or doubt, please feel free to raise it. Please feel free to unmute and ask that doubt. So we are having around 20 questions for today's session. So first we are going to be dealing with a singly reinforced beam without the compressive load, and then we are going to take up a singly reinforced beam with axial compression of different axial compression ratios, and then finally we are going to take a doubly reinforced concrete beam. Okay, so let me start out by drawing the cross section of this particular beam, right? So we have rectangular RC beam. So it is having a width of 250 mm and the overall depth is 250 mm. And reinforcing steel is provided only in the tension region. Let's call that as AST. So that is four rebars of 20 mm diameter. So that turns out to be 1256.64 mm square, provided at an effective depth of 450 minus 50 millimeter. Yeah, effective curve 50 millimeter. So that is 400 millimeter. And we know that F prime C is 30 MPa, and the reinforcing steel, the tensile strength is, the yield strength is 500 MPa. Okay, so what is the procedure to calculate the ultimate moment capacity and the ultimate curvature? So in order to calculate the ultimate moment capacity and the ultimate curvature, can you let me know what is the strain in concrete that we're going to consider?
0.0035, sir.
Yeah, exactly. Yeah, thanks for the response. So we're going to consider 0.0035 as the strain in concrete, right? So I'm going to be solving this using two methods. So first is we are going to solve it using the regular equations. Then we're going to confirm that with the Excel sheet also. Okay. So I'm going to, yeah, we already have the cross section over here. So we're going to take epsilon C is equal to 0.0035. Then we need to assume a value of x, right? Assume the value of x so that the compressive force in concrete is equal to the tensile force in the reinforcing steel, right? So before that, in order to evaluate the parameters of the stress block, we need we need the parameters of the stress block in order to evaluate the compressive force, right? And that is alpha 1 and beta 1. So how do we find out the value of alpha 1 and beta 1? First, we're going to find out the value of beta 1, right? So beta 1 is given by 4 minus epsilon c by epsilon prime c divided by 6 minus 2 times epsilon epsilon c by epsilon prime c. So we know that epsilon c for the current case is how much? For the current case, it is 0.0035. And what would be epsilon prime c?
0.002.
Yeah, exactly. Exactly, it is 0.002. So when you solve this, we get the value of beta 1 as, were you able to, sorry?
0.9.
Yeah, so zero point 0.9. So we get the value of beta 1 as 0.9. And then let's proceed to find out the value of alpha 1. Alpha 1 is 1 over beta 1 into epsilon c by epsilon prime c minus 1/3 of epsilon c by epsilon prime c whole square. Okay, so we get the value of alpha 1 as,
0.81.
yeah, exactly 0.8102. So we are solving this using the formula explicitly, because so that we can recap the concepts, but for higher values of strain values, in order to develop the moment curvature plot, we're going to be going to be using the Excel sheet, which I'm going to show you in a little while. So from this, let us calculate the value of the effective, the compressive force. Before that, we need to assume the value of x, or the depth of the neutral axis. So for this particular problem, I got that we need to consider the value of x is equal to 114.9 millimeter. Okay, 114.9 millimeter. So for that we have Cc is equal to alpha 1 f prime c into beta 1 into x into b. That will give us the value of Cc. So let us plug all the values and see how much Cc we are going to get. 0.81 into f prime c is 30, and beta 1 is 0.9 into 114.9 into uh, b is 250. So what is the value of Cc we are getting?
Six 28.
Yeah. So thanks. Yeah, thanks for the response. So we get the value of Cc as 628.4 kilonewton. Yeah. And then we need to find out the value of Ts. So Ts is simply Fs into As. So how do we find out the value of Fs? We're going to be we're going to first calculate the value of strain, right? So we're going to consider the linear distribution of strain along the depth of the cross section. Okay, this is epsilon c. This is the x value assumed. This is epsilon s. I'm going to take a different color for better contrast. So we have epsilon c by x is equal to epsilon s by b minus x. Okay, so let us substitute 0.0035 divided by 114.9 is equal to epsilon s divided by b is 400 minus 114.9. So what is the value of epsilon s?
Point double zero eight.
Okay, 0.008. Yeah, but we know that this is greater than 0.0025,
So,
which is greater than the yield strain. So we'll take Fs as 500 MPa. So we'll get Ts as 500 into 1256.64, which gives us a value of, it has to be equal to Cc, 628 point.
620.
Yeah, six. It can be like slightly, the point value can be slightly higher or lower by zero point 0.1 or zero point 0.2. Um, so once we got the equilibrium of the forces in the cross section, we'll find out the value of m, right? So there are various values for finding out the value of the this thing. So I will just utilize, taking moment about the tensile reinforcement, that is Cc into d minus beta 1 into x by 2, right? So from that, what is the value of m that we get? So would you like to respond?
We're calculating.
Yeah, sure.
One one
Please go.
It's 628.4. 19.
So I'm getting a value of 2219.
Sir,
Yeah, yeah. So
219.
yes, 219 kilonewton meter. And the value of curvature, ultimate curvature, that is epsilon c by x, epsilon c by x. So this is the curvature. So I'm getting a value of, uh,
It's 2.6.
yeah, you may please confirm that
3
later.
point
Yeah,
3
30.5.
point 10 to the power of minus 6.
Yeah, exactly. 30.5. So yeah, when we go back, sorry. So when we go back to the options, we see that option D is the correct response. Okay. So we'll try to solve this using the Excel sheet also. Okay. So I hope that my Excel sheet is visible.
Sir,
Okay. So it is, I prepared this last year when I was being the TA for the same course. So again, it is pretty straightforward. So you substitute all the input values, right? So we have B is equal to 250, D is 450, effective depth is 400, and the area of steel is 1256.64. It will automatically calculate the percentage of the tension steel. Then F prime C is the cylinder compressive strength. Epsilon prime C is the strain corresponding to F prime C, right? And then Fy is the yield strength of the reinforcing steel. And this is the percentage actual force. So we are going to consider 0 for the present problem. And then we need to assume the strain in concrete. So for the present case, we are considering the ultimate moment capacity and the ultimate curvature. So the corresponding strain is 0.0035. So corresponding to that, we can calculate the compressive force over here. So we are evaluating the alpha 1 and beta 1, that is the stress block parameters based on the uh, compressive strain in the concrete. Then here we are going to calculate the strain in the reinforcing steel, and then depending on uh, whether it is yielded or not yielded, we are going to calculate the corresponding stress in the tensile reinforcement and the tensile force. Then essentially what we are doing is we are evaluating whether the forces are balancing or not. So as you can see presently, the compressive force is significantly higher. So we need to reduce the value of x. So we can reduce it to 220 and see. Uh, Actually, I had already evaluated the x value. So just let us try to input some numbers and see what will be the implications on the compressive and the tensile force. So again, Cc is higher. Let us reduce it little more. So 190, 180, still it is higher. Let us increase it a little further, 160, 140. So we are seeing that the tensile force and the compressive force, they are somewhat converging. So as you can see, the TS is now has reached the constant value because the rebar has already yielded. So once it has yielded, it will not take up additional stresses or forces. However, you can increase or decrease the compressive force by varying the depth of the neutral axis. Okay, now let us consider for 120. So CC is 650 and TS is 628. So let us make it 115. So we are close to it. So I considered 114.8. So we are able to achieve the tensile force as 628 and the compressive as 628. So once we achieve the balance, we'll go ahead and calculate the value of the moment capacity, right? So as you can see here in this equation, I've considered the moment capacity by considering the mid height of the cross section, and then the curvature is there. So yeah, so this is how. So first we did by the calculation method, and then we are going to verify that using the Excel sheet. So once we have sort of verified or validated this Excel sheet through hand calculation, then for further values, we can just go ahead and solve it using the Excel sheet. So I think the first problem is clear. Then we can proceed to the next problem. Uh, so, yeah, second problem is for the beam given in question one, uh, excuse me, for the beam given in question one, the existing reinforcement is replaced with 5 HYSD bars of 25 millimeter diameter. If the beam is tested under 4-point bending up to failure, which type of failure is expected? So I request you to think for a minute and let me know how we can solve this problem. Okay, so we can solve it together. So are you able to come up with a way of determining the solution? Kindly let me know. I'm going to draw the cross section in the meantime.
Think we have to assume X after we have to find a strain in reinforcement. If reinforcement strain is 0.00 less than 0.0025,
Yeah,
then we can find out it is compression control or balance or tension control like that.
yeah, exactly. I think you have spotted exactly how it needs to be done. Uh, so that's a good answer. So I will go ahead and solve the problem now. So essentially, what we are doing is we are going to calculate the area of steel for the balance section. Okay, so what will be the area of steel corresponding to the balance section? So we are going to compare the balanced reinforcing steel along with the steel that is actually provided. So compared to the balanced reinforcing steel, if the provided steel is more, that means it is over reinforced. So it will undergo brittle failure. On the other hand, if the area of steel provided is less than the balanced steel, then it is going to undergo a ductile failure. It is under reinforced. Okay, so that is the concept, and I think the participant also, he got the concept correct. So we can start, go ahead and solve the problem now, right? So we have the cross section over here. So what we are doing essentially now is we are going to calculate the steel for the balance section. So let me write it here, exactly what we are doing. Steel for balanced section. So what is the definition of a balanced section? Balanced section is one where the crushing strength of concrete, sorry, the crushing strain of concrete and the yielding strain of the reinforcing steel happen simultaneously. Sorry, sorry for that diagram. It has to be linear, as you might know. So once we're able to crack this concept, the problem becomes quite simple. Uh, okay, and we have the effective depth as 400 millimeter. So as I was telling, balance section is one where the crushing strain of concrete 0.0035 and the yield strain of the reinforcing steel, that is 0.0025, they are attained at the same time. Okay, that is the concept of the balance section. So once we find out the area of steel corresponding to the balance section, then we will compare with the provided AST, with the AST provided. So I'm taking a different color. So here we have X, and here it is D minus X. Okay. So we already know the value of strain. We know the equation, epsilon C by, sorry, X is equal to epsilon S by D minus X. So we know all the values, 0.0035 by X is equal to 0.0025 divided by 400 minus X. So we need to find out solve the equation for X. X is, are you able to calculate?
3.33.
Uh, okay, so
233.33.
yeah, exactly. So getting a value of 233.33 millimeter, that will be the depth of the neutral axis. And we already, yeah, so we need to find out the area of steel. How we are going to solve that? Equating the compressive force and the tensile force, right? And we know CC is alpha 1 F prime C beta 1 into X into B, and this is Fs into AST. Okay, so alpha 1 and beta 1 we know from the previous problem. We are, I'll take a different color. So we know that for, F prime C is equal to 30 MPa, and epsilon prime C, sorry, epsilon C is 0.0035. We know that the value of alpha 1 and beta 1. So alpha 1 is 0.81 and beta 1 is 0.9. Okay, so when we substitute all these values, we have 0.81 into 30 into 0.9 into 233.3 into 250 is equal to 500 into AST. So solving, can you please tell me what is the AST that we are getting?
2551.
Okay, thank you for the response. So AST is 2551 mm square. And now let us calculate the AST provided. Okay, so for a balanced failure, 255.1 millimeter square, that is the area of steel that corresponds to a balanced section. So if it is less than that, it is under reinforced. Okay, if it is under reinforced, it will undergo tension control failure mode. And if it is more than that, then it is over reinforced. Okay, in that case, it will go a compression control failure, where the crushing of concrete takes place before the yielding of the reinforcing steel. So let us find out the AST provided. So that is quite straightforward. What you do is just pi by 4 into 25 square into 5. So what will be the AST provided? Can you please tell me, let me know? So yeah, you may please verify that.
453.
Yeah, exactly. So it is 2454 mm square. That is the AST that is being provided. So this is slightly lesser than the AST corresponding to the balance section. Okay, so it is under enforced and it will undergo a tension controlled failure mode. So option C is the correct response. So I'm going to write down it correctly over here. So the solution is AST provided is less than the AST corresponding to the, so it is under enforced tension controlled ductile failure. Okay, so I think with that we can proceed to the next question now. So it is a straightforward conceptual question. So when a beam is subjected to flexure along with axial compression, which of these equations represents the force balance equation for the cross section? Okay, kindly let me know what would be the answer.
This is A, sir.
Option A.
Yes, sir.
Okay. Okay, thank you for the response. Let us see what is the answer. Yeah, so exactly. Option A is the correct response. So as you might have seen in the class, so when we consider a beam that is subjected to uniformly distributed load and uh, a lateral load, concentrated load, along with the compressive force, when you take a cross section over here and when you consider the force balance equation, we see that the tensile force in the rebar and the axial force on the beam, they act in the same direction. And in the other direction, we have the resultant compressive force from the concrete. So whenever a beam is subjected to axial compression, please remember that when it's subjected to axial compression, then this equation holds good. But if it is subjected to axial tension, then basically this becomes minus P. So basically P will for tension, P acts in the left direction. So then the equation becomes C Cc plus P is equal to Ts. But for compression, this is the correct equation. Um, so we can proceed to the next question now. So this is a numerical problem that we are having. So I'm going to read out the data, then we can start solving the problem. So consider a beam. Let me take the pointer. So consider the beam of dimensions 250 by 450 millimeter overall depth. The concrete has a mean cylinder strength of 30 MPa. The beam is reinforced with 4 bars of 20 millimeter diameter on the tension side with an effective core of 50 millimeter. If the beam is subjected to axial compressive force of 0.1 into F prime C into AG, that is 10% of the axial capacity, what is the moment of resistance and curvature of the cross section corresponding to a concrete strain of 0.0005? Okay. So before starting the problem, I would like to ask the participant whether you have prepared an Excel sheet for this.
No, sir, I don't have Excel sheets.
Okay. Okay. So actually, Excel sheet, as I demonstrated in the class earlier, it becomes very easy for you to uh, do the iterative calculation to take the value of x and solve. So I encourage you to make your own Excel sheet. So if not, like I'll be happy to share that. So uh, so you can I think I can give the value of x and probably you can try to attempt the problem. So as I mentioned earlier, first problem we are going to do using the hand calculation, and later on we can, for the higher values of concrete strain, we can solve using the Excel sheet. Uh, okay, so one hint that I can give is the value of x is, I got it as 243.5 millimeter. So you may please go ahead and solve the problem and obtain the value of the um, moment of resistance and the curvature. Okay, so this x is the depth of the neutral axis, as it be aware. So I'm just going to explain very briefly. Okay, so we have the cross section over here. Right. And so if you, there is a proper algorithm, to solve these problems. So I gave the steps in the previous class also. So I'm just going to iterate that one. So take a certain value of epsilon c, then assume the value of x and make sure that, so whenever there is a beam, reinforced concrete beam under compression, it needs to satisfy this equilibrium equation, that is ts plus p is equal to cc. Yeah. So once we get the value of x, then we can go ahead and calculate the value of m and the curvature. Okay. So I'm going to solve it very quickly. We have epsilon c is equal to 0.0005 epsilon x, and then this is d minus x. So we know that yeah, d is equal to 400 millimeter. F prime c is 30 MPa, and Fy is 500 MPa. So let us calculate the value of the axial force. So axial force is given as zero point 0.1 F prime C into AG. So that would be zero point 0.1 into 30 into gross area is 250 by 450. So what would be the value of P?
337.5.
Yeah, yeah. Thanks for the response. So P would be 337.5 kilonewton. Uh, so we need to, balance. We have on one side, we have ds plus P, right? That is on one side. Then we have Cc. So for the compressive force, we need to find out the value of the stress block. We need to find out the stress block parameters, alpha 1 and beta 1, and corresponding to corresponding to epsilon prime c, sorry, epsilon c as 0.0005. I'm just going to make use of the Excel sheet because by now, we know how to calculate. So alpha 1 is 0.336 and beta 1 is 0.6818. 682. Okay. From here, we need to equalize these two values. So I already gave a hint that for x is equal to 243.6 millimeter, x is 243.6 millimeter, we're able to achieve the equilibrium. So let us calculate that, and so let us find out for Cc. So Cc is equal to alpha 1 into f prime c, beta 1 into x into b. So what would be the value of Cc? Can you please let me know? Right. For
Sir, 418.48.
okay, let us see 418.5.
Hmm.
Okay, so let us check. No, yeah, I'll just confirm with you. Yeah, thanks for the response. I too am getting kilonewton. Like, let us proceed and see what you're getting. Uh, were you able to calculate the epsilon s? If yes, let me know.
Triple zero 32.
Okay, point triple zero 32, is it? Okay, let me just check. So I think we need to add one more zero over here. So that is, yeah, I think you mentioned right. I think I missed one zero over here. So what would be the Fs? Fs would be epsilon s into Es, right? Into 2 into 10 to the power 5. That gives us 64.2 kilonewton. Sorry, MPa. Fs is 64.2 MPa. So let us write, calculate the value of Ts plus P. So Ts plus P is 64.2 into area of steel is again 1256.64 plus P is 337.5. So can you please tell me what is the value of Ts plus P? So you can please verify later on. I'm getting the value of Ts plus P as 418.2 kilonewton. So for an RC beam subjected to the axial compression force, we are able to achieve the equilibrium between the tension force, the combination of tension in the rebar and the axial force and the compressive force. So from this we can go ahead and calculate the moment capacity and the curvature, right? So we can take the I'm going to take a different ink for better contrast. So we are going to take the moment capacity about the mid height of the cross section. Okay, d by 2, because we know that the axial compression acts through the centroid, that is P. So we are going to consider the mid height of the cross section in order to evaluate the moment capacity. So M is given by Ts into d minus capital D by 2 plus Cc into d by 2 minus beta 1 into x by 2. So can you please tell me what is the value of the moment that we are getting? I'm also calculating along with you. So I'm getting a value of 73.4. Yeah, 73.4. So please verify this value later on. So the M is 73.4 and the value of phi is x by sorry, epsilon c by x, very sorry, epsilon c by x, that is 2.05 into 10 to the power minus 6. Okay, now let us go back to the options and see. Yeah, so option C matches quite well with the values that we are getting. Okay, so I hope the procedure is clear for the participant.
Yes,
Yeah, okay, yeah, thanks, thank you. Um, so once we have got this, let us see what is the next problem is. Okay, so for the beam given in question 4, what is the moment of resistance and the curvature of the cross section corresponding to the concrete strain of 0.001? Okay, so now what we are going to do is, as in the previous live session also, we did the same format, right? So we are going to consider different values of strain in concrete, actual strain in concrete. Then we are going to calculate the moment capacity and the curvature, the moment of resistance and the curvature corresponding to different strain in concrete. And then once we have the values, curvature 5, moment, we're going to plot the moment curvature plot. So we have epsilon c as 0.0005, 0.001, 0.0015, 0.002, and ultimately 0.0035. So let us go ahead and see. We already got for 0.005 what is the m and phi. So here we actually took help of the equations and we determined the values of m and phi. Again, the algorithm is, it is there. Let me block it off using uh, another color. Yeah, so this is the algorithm that we follow. So we consider a particular value of epsilon c, assume the value of x, then we uh, carried out this iteration until we were able to achieve the force equilibrium in the cross section. Then based on the equation, that is m is, we took the moment about the mid height of the cross section. So the moment of resistance is given by Ts into d minus capital D by 2 plus Cc into d by 2 minus beta 1 into x by 2. So from that we get the moment of resistance. Then we get the curvature of the cross section. Phi is equal to epsilon c by x. And then we carry out this procedure corresponding to different values of epsilon c. So in the previous problem, we calculated m and phi for epsilon c of 0.0005. Now we'll calculate for 0.001. Okay. So now we know the value, we know the concept. We're going to take the help of Excel sheet directly. But I suggest you to, do it manually also, at least for one problem, and try to validate your Excel sheet uh, based on the values you get uh, from the actual formula. So, okay, let us go to the Excel sheet now. So, the width of the beam is same. Overall depth is 450 millimeter. Then the effective depth is 400. AST is 1256.64 mm square. Percentage steel is automatically obtained. F prime C, cylinder strength 30 MPa. Epsilon prime C 0.002 corresponding to F prime C. Fy is 500 MPa. and we have the axial compression is zero point 0.1. Okay, so it is zero point 0.1, and the strain in concrete is 0.001. So we can see that the value of Cc is lesser than Ts plus P. So we'll increase the value of X. Let us go to 120. We need to increase it further. Let us make it 140. So it is 440 and it is 804. We need to increase it further. 160. So it is 500, and here Ts plus P is 740. Let us increase it further. 170. Okay, so we are getting closer. 180. Further. 200. Okay, so now we see that the Cc has increased. So the value has to be between 180 and 200. Let us try for 190. So we need to increase Cc slightly. 195. Okay, so we increased it too much. So 193. Okay, increase it slightly. 193.5. Okay, I think we can go ahead with this value. So we get the value of X as 193.5. So once we have the value of X, we can find out the value of Cc, and then uh, the value of Ps plus P, and then find out the value of M and phi. So, I'm getting the value of M as 142 kilonewton meter, value of phi as 5.17. So option B is the correct answer. Um, so I hope the participant was able to understand the calculation that we did using the Excel sheet.
Yes, sir. Yes, sir.
Yeah, so I suggest you also to participate in the next problem, so we can locate the neutral axis together, and then we can proceed to find out the moment capacity and the curvature. So I think we can start actually making the entries in this table, so that uh, we can actually start making entries, so that we'll see what we get later on. Mm, okay. So 0.005. So for this we got 142, 142, and phi is 5.16. Yeah, and please note that P is zero point 0.1 F prime C into Ag. That is 10% of the axial capacity. Mm, for 0.005 we get 74 and 2.05. 74 and 2.05. Now let us proceed to find out the M and phi for 0.0015. So it is very straightforward. So I encourage you to prepare the Excel sheet. If not, I can share it with along with the PDF of today's PPT. I can share that. So now CC We need to increase x or we need to decrease x?
Please, sir.
Uh, yeah, so we need to decrease. So let us try for 190. So now we need to decrease, increase or decrease?
But still decrease.
Yeah, yeah, thank you. Uh, so now we need to slightly decrease, right?
Yes, yes.
184.5.
77877.
Okay, so it is, we can slightly decrease. Let us see what happens. Yes, I think zero point
Okay.
0.15. Yeah, I think now it is, it is good enough. Uh, yeah, so we were able to balance the compressive force and then PS plus P. Correspondingly, M is 200.36 and 8.13. 200.36, 8.13. So uh, it is quite evident that option D is the correct response. So 208.14. So all these values are with respect to 10 to the power minus 6 per millimeter. And this is with respect to the kilonewton meter. So let us proceed and solve the problem. So option D is the correct response. So let us find out what would be the values of m and phi corresponding to epsilon c of 0.002. Okay. So should we increase or decrease now?
A little bit increase.
Yeah, yeah, exactly. I'm surprised that, for this value of strain also, the value of x is somewhat closer to the previous value. 185. Okay, decrease 184.5. We need to increase slightly. 184.6. Increase it slightly. So we need to decrease it slightly. Right, 184 point. Yes, I think we can, keep this value. X as 184.7. X is, yeah, sorry.
No. Yes, sir. Yes, sir.
Okay, okay. X is 184.7. So correspondingly, M is 246.4 and 10.8. So let me change the precision of this uh, scientifically. Okay. 246 and 10.82. Yeah, so option A looks like that's the correct answer. Let's go back and make the entry. Sorry. Okay, so we need to find out the Mn5 corresponding to the uh, maximum compressive strain. Okay, so we got a difference now. So now should we decrease or increase the x value?
Decrease,
Okay,
decrease.
okay. So let's decrease 180, decrease even further, 178. Okay, slightly increase, 76.5. Yeah, I think we can stop at this. Again, we can go ahead, we can achieve, double up to the second decimal point accuracy, but I'm going to stop it because once you have your own Excel, once you have Excel sheet with you, when you are practicing, I think you can go ahead and go for more accuracy. So let us stop at this point. X is 176.5. And the value of M and phi that we get are 250.5 and 19.8. Yeah, so option C gives us the correct answer. So here, actually, you can see, you can make out the trend that as we increase the compressive strain in concrete, it is increasing from 74 to 142 to 200. And at the compressive strain of 0.002, we can see that the moment capacity is getting saturated. So it is getting 246 somewhere here, and ultimately it reaches a value of 251 only. Okay. So we can say that if you consider the yield point of the entire beam for the reinforced concrete beam, then the yield point would be close to this value, corresponding to M of 246, and the curvature is 10.8. So we look at the plot in detail in the upcoming slides. So once we have plotted, uh, once we have obtained the values of M and phi corresponding to the different values of uh, the strain in concrete. So the next question is plot the moment curvature graph for the beam given in question 4 based on the results obtained from question 4 to question 8, and compare this with the moment curvature curve when no actual force is applied. So that is corresponding to which question? Question 1. Okay, so the difference between question 1 and question 4 is that we took 10% actual force here. Here there was no actual force. So in the previous week also, in week 5 of the live interaction session, so in week 5, we did the same uh, we did the same exercise and we plotted the moment curvature plot. Okay, so let's look at the plot now. So here the plot which is represented by this orange color graph, so that corresponds to the beam when no actual compression is applied. But the moment curvature plot corresponding to this blue is represents the moment curvature plot when 10% actual compression is being applied. So what we can observe from these two plots is that when you apply the actual compression, when you apply the actual compression, the moment capacity increases, but the curvature decreases. Okay, so it is we have established in the previous class also. So when we do the analysis, if the moment capacity is high, we need to increase the moment capacity. We need to increase its capacity by design, right? But it should not come at the cost of the curvature. Okay. So the curvature also, it has to be the curvature has to be high in order to ensure a ductile behavior of the reinforced concrete beam. So what we can say is that yes, the actual compression is good for the moment capacity, but it should not compromise the curvature of the beam. Okay. So we look at another problem now. Okay. So consider the beam given in question 4. If the beam is subjected to an actual compression of 20% of the actual capacity, what is the moment of resistance and the curvature of the cross section? Okay. Can you try solving this problem? Okay. Just take a few minutes. Okay. I will start solving the problem simultaneously. Right. So at this point, I would like to ask the participant, like, would you like to take a break of, let's say, 3 to 4 minutes, or we can proceed with the session?
No problem, sir. Yes.
Sorry.
Okay, no problem, sir. We can take break.
Okay, okay, okay. I think because of continuously speaking for like 1.5 hours, like I need a few minutes. We can resume the class
Okay, sir.
at 7:30. Okay.
Okay, 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 sir.
Yeah.
Thank you.
Yeah, so welcome back. I think we can start the session now. So I was just looking at the remaining problems for today's session. And yeah, presently we are in the 10th problem. So we have another 10 questions for today. So without any further delay, I think we can start the session. So I hope that my screen is visible.
Yes, sir.
Okay, okay, thank you. So now what we have done is we have considered a beam with RC beam with no axial compression. Then we considered RC beam with 10% compression. Then we'll do for 20%, 30%, 40 and 50. I think 50 is there, 50%. And what is this 10%? It is nothing but zero point 0.1 F prime C into Ag. Okay. So for this, we considered for different values of compressive strain, that is epsilon C is 0.0005, 0.001, 0.0015, 0.002, and 0.0035. Now, for all these, axial compression, we are going to find out only the ultimate capacity uh, corresponding to the ultimate strain. Okay, but I have, already done corresponding to different strain values in order to obtain the plot. But now, for the sake of today's live session, let us go ahead and solve uh, the problem in order to obtain the moment capacity and the curvature corresponding to different axial compression ratios corresponding to concrete strain of 0.0035. Okay. So again, I'm going to solve only in the Excel spreadsheet. Okay. So again, as I mentioned, the dimensions of the beam remains the same. Yeah, so the dimensions are the same. It is having a depth of width of 250 millimeter, overall depth of 450 millimeter, and the effective depth of 48 millimeter. Then the area of steel is 4 rebars of 20 millimeter diameter. Let us go to the Excel sheet now. Yeah, so B is 250, capital D 450, effective depth 400, A stays 1256.64 mm square, PST is automatically calculated, F prime C is 30, epsilon prime C is 0.002, Fy is 500. Now P is changes from 0.1 to zero point 0.2. Okay. So the corresponding axial force is 675 kilonewton. Epsilon C is 0.0035. Now, as Cc is less than Ps plus P, we need to increase or
Increase,
decrease? Yeah, increase. Absolutely right.
increase, sir.
Yeah, absolutely right. So 180, 200, let us increase further, 210, increase further, 220, increase little further, 230, increase further. So as you can see, the reinforcing steel it has yielded. It has crossed the value of 0.0025. So the Ts plus P is not going to increase any further. We need to achieve the equilibrium only by increasing the depth of the cross section. Okay, that is the only way. Let us do for 235. Okay. Okay, now we need to increase it slightly more. 235, right? 36. Okay, it is crossed now. 235.7. Yeah, I think now it is agreeable, though it is not exactly accurate. But I think we can still go ahead, for the purpose of today's class. So the corresponding moment capacity and the curvature are 260.6 and 14.8. Right. 260.6, and so option B gives us the correct answer. Yeah, option B is the correct answer. Now let us calculate corresponding to epsilon C of 0.0035 and axial forces 0.3 F prime C into Ag. We have to find out the value of M and psi. So let us first calculate what is the axial compression force, that is 1012.5 kilonewton. 1012.5 kilonewton, right? So we need to increase C or decrease C here.
Increase, sir.
Yeah. Okay. So to increase it further, increase further 265, increase a little more 268. Okay, increase 266. Okay, we can stop at this point. So we are able to achieve the equilibrium 1455 and 1455. The corresponding M and 5 are 230.7 and 13.15. 230.7 and 13.15. So option E is the correct answer. Let us proceed further. Now, corresponding to epsilon C is 0.0035. So we are calculating the ultimate moment capacity and the ultimate curvature, and the axial compression is P is 0.4 F prime C into Ag. So what is the corresponding axial compression force? It is 1350 kilonewton. 1350 kilonewton. Okay. So do we need to increase or decrease?
increase.
Yeah, because as we can see here that the tensile force and the axial force that is increasing because we are increasing from point 0.1 10% to 20% to 30%. So in order to balance this component, that is Ts plus P, we need to increase the value of the uh, compressive force by increasing the depth of the neutral axis. So let us try 280. Okay, increase further 285, further 290, right? Uh, Increase further 295, increase further 298. Okay, further 300, little more 301. Wait, we need to decrease now 305.5. Oh, 300. Okay, I think we can stop at this point. For x value of 300.2, the corresponding moment capacity and the curvature are 198.8 and 11.7. So I think option A is the correct answer. And finally, when we increase the actual compressive force, so let us keep in mind that we started with no axial force to 10% to 50%. Okay, so this is actually very high. So this we can say that it is uh, behaving like a beam column member, right? So beam column member is one which has considerable flexural load plus axial load. So now corresponding to epsilon c of 0.0035 and p of 0.5 f prime c ag, let us calculate the corresponding moment capacity and the curvature capacity. So P here is 1687.5, 1687.5 kilonewton. Let us see what is the value of X we are going to get. So in order to balance the TS plus P, we need to increase the value of CC. Let us try for 310, further 320, increase it further 330, sorry, increase it slightly more 335, slightly more 336, 337, 338. Yeah, we can stop it here. X is equal to 338 mm, and the corresponding moment capacity is 163 and 10.4. So option C is the correct answer. Now, now we have seen that we need to plot the moment curvature plot for the beam given in question 4 corresponding to different levels of the axial force that are being applied, right? So this is the moment curvature plot that we are getting. So this actually, it consists of so many data points. So this is uh, corresponding to no axial force, that is P is equal to 0, and this is P is equal to 10%. So totally in this graph, we are having almost 25 data points where we have plotted the moment curvature graphs corresponding to different values of axial compression, right? And what we can see here is that when we increase the axial compression, initially up to corresponding to uh, 10%, okay, corresponding to 30%, there is an increase in the moment capacity. But as you can see, there is a very drastic decrease in the curvature of the beam. So the curvature of the beam drops from 30 into 10 to the power minus 6 to 20 into 10 to the power minus 6. So there is almost 33% reduction in the curvature. Okay. So there is almost 33%, which means that it is transitioning from a ductile behavior to a not so ductile behavior. So can the participant tell me what do they understand by the meaning of ductility from these plots?
Ductility reduced, sir. Brittle mode increase.
Yeah, so can you tell me by looking at this
When
plot how you can actually
yes,
quantify the value of ductility?
when we increase axial force, ductility is getting reduced.
Yeah, so
I'm not getting.
yeah, so I can tell you. So yeah, you can. So when we, for example, as research students, we tend to perform experiments in the laboratory. So what we do is, when we test the beam, so we are going to test the beam over here, consider some supports, and then we test them under the monotonic loading. Then we monitor the value of axial force, and then we monitor the displacement also. Okay, so then we measure this ductility. So this ductility is represented by delta. Delta is, or mu is given by phi u by phi y. That is the ratio of ultimate curvature to the yield curvature. So here you can see that the ultimate curvature is 30, and the yield point is when the relation becomes linear to a plateau. So up to here, you can see that the moment and the curvature, it is increasing proportionally. So it is maintaining a linear relation. So beyond that, it becomes non-linear. It becomes a plateau. So this is delta y. So the value of delta u by delta y, that is the technical definition of ductility. So whenever we are designing a reinforced concrete beam or a column, we need to design it for high ductility. Okay? So essentially, what we are meaning is that, like, when we are imposing certain axial load, it is it is beneficial, you can say, up to like 10% axial force. But beyond 10% axial force, we can see that the moment capacity is also moment capacity is increasing up to 30%, but for 40% the moment capacity is decreasing and the curvature is also decreasing. Okay, so that is what I wanted to convey using this plot, that increasing the axial capacity, it is beneficial from the moment capacity point of view, but from the curvature it is not good. Okay, and whenever you have a very low curvature, then it is not going to behave in a ductile manner. That is not the kind of behavior we desire from a reinforced concrete structure. Okay, so we can proceed to the next question now. So sorry. Yeah, so I think this conceptual question sort of explains the behavior, the moment curvature behavior in a better way. So which of these statements can actually describe the influence of the limited axial force on the moment curvature of the singly reinforced beam? Okay. Kindly take a few seconds and let me know what is the correct response.
C, sir. Axial force increase the ultimate capacity but decrease the curvature capacity.
Yeah. Thank you for the response. And as you said, like option C is exactly, absolutely the correct answer. And we saw that in the previous plot also, that if you increase limited axial force, sorry, if you're increasing up to, let's say, around 10% to 20%, there is an increase in the ultimate moment capacity, but the curvature decreases. So as you rightly mentioned, option C is the correct response. So the next question is, how is the effective reinforcement ratio of a doubly reinforced beam expressed if rho is the reinforcement ratio on the tension side and rho prime is the reinforcement ratio on the compression side? Effective reinforcement ratio. Uh, can you attempt the answer? Okay. So option B is the correct response. So this is, let us say that you have provided 4% on the tension side and 2% on the compression side, right? So the effective reinforcement ratio, or like rho effective, is rho minus rho prime. Rho corresponds to the tension and rho prime corresponds to the compression reinforcement. So now, once we have tackled the reinforced concrete beam subjected to axial compression, we are going to start solving problems on the reinforced concrete beam which are doubly reinforced. Okay. So kindly take a few seconds to solve the problem. Even I'll be solving the problem simultaneously so that we can obtain the correct answer. Okay. So now we have the doubly reinforced beam. I'm going to draw the cross section now. Okay, so I think we already have the cross section. Let us take the help of this. So the objective of this problem is to determine the moment capacity and the curvature corresponding to a concrete strain of 0.0005. Okay, let us quickly start with the hand calculations now. First, I'm going to draw the strain profile. So here, in addition to the concrete and steel rebar, we have the steel in compression as well. Okay, so I request you also to start solving the problem. We can do it together. Okay, now we need to balance the compressive and the tensile forces, that is Cc plus Cs should be equal to Ts. So I'm going to give a hint that corresponding to x is equal to 130.1 mm, we were able to achieve the equilibrium. Okay, so we'll just quickly start, and try to solve the problem now. Sorry. So 400 minus 130.1 gives us a value of 269.9 millimeter. So what is the value of epsilon st? Can you please let me know?
10010.
Yeah, thank you. I'm getting expressing in terms of 10 to the power minus 3, right? So correspondingly, we have fst is equal to epsilon st into es, that is
207.
yeah, thank you for the response, 207.4 MPa. Okay, okay. Now we have epsilon sc by mm, epsilon c by 130.1. So this is 130.1 minus x, sorry, minus 50. Sorry about that. So this is we are getting from similar triangles. Okay. So epsilon c is 0.005. So from this, what would be the value of epsilon sc? So 50 divided by 130.1 into 0.0005. 3.08 into 10 to the power minus 4. Please check these values later on, minus 4, and multiply by 2 into 10 to the power 5, that is 61.6.
80.1.
Okay, yeah, please check these later on. Okay, so from this we need to uh, calibrate, I mean, we need to equate, obtain the equilibrium. Okay, so corresponding to this, we need to obtain the stress block parameters, right? So let me take a different ink. Okay, so I'm going to solve here. CC is alpha 1 F prime C, beta 1 into X into B, plus FSC into AS is equal to TS. TS is FST into AS. Uh, I'm going to take the help of the Excel sheet, to calculate that. Or well, I think since it's the first problem, I think we can also do it manually. Okay. Alpha 1, alpha 1 is 0.34 and 0.68. You'll have to excuse me. I'll have to take the help of this space only. Into X is 130.1 into 250. Okay. Plus FSC is 61.6 into AC is 600, right? Yeah, 600 is equal to FST is how much? 207.4 into 1256.64. Sorry about that. Can you please check if we're able to balance the two forces? 34 into 30 into 68 into 130.1. Yeah, somewhat approximately, but it should be fine. 260.7. So we are able to balance the compressive and the tensile forces. Okay. So we can go ahead and calculate the moment capacity and the curvature. So M, what I'm going to do is I'm going to calculate considering the level of the tensile reinforcement. Okay. So M can be found out using this equation Cc into d minus beta 1 into x by 2 plus Cs into d minus d prime. Okay, and phi is, as we know, epsilon c divided by x. So from that, what is the value we are getting? So after calculation, I got the value of m as 92.5 kilonewton meter and phi as 3.8 into 10 to the power minus 6 per millimeter. Okay. So I request you to just, solve, use this equation, plug all the values and see if you're getting this answer. Okay. So option A is the correct response. So we'll move ahead, right? And we are going to solve the rest of the problem using the Excel sheet. We have another 3 problems for today's session. So I hope it is fine. We are going to exceed by another 5 minutes. So we are
Yes,
going
sir.
to take
Okay.
another 5 minutes to solve to complete today's problem. We started 5 minutes late. Okay. So kindly bear with me. Okay. So for for the beam given in question 17, what is the moment of resistance and the curvature of the cross section corresponding to concrete strain of 0.0035? Okay. So again we have this cross section. I'm going to draw once again, and we did the calculation using uh, we did using the manual calculations in the previous part of the problem. Now I'm going to show how to solve the problem using the Excel sheet. Okay, AC. Okay, so here B is 250 millimeter, and overall depth is 450, right? And here the effective depth is 400 millimeter, and then the effective depth for the compressive reinforcement is 50 mm. Okay, and AC is 600 mm square, and AST is 1256.64. Okay, now uh, we will go ahead to the Excel sheet. So here actually the Excel sheet that I have prepared for the doubly reinforced cross section is slightly different when compared to the one that I prepared for the axial force, because here there is an additional component of the reinforcing steel in the compression area. Okay, so here the width is 250 millimeter, overall depth is 450, and the effective depth is 400, and AST is going to be 1256.64. Okay, and we have the percentage of steel in the tension automatically. Then the AAC is 600 millimeter square, and we get the percentage steel in compression automatically. And the effective depth of the for the compressive reinforcement is 50 millimeter. F prime C is 30. Epsilon prime C is 0.002, right? Fy is 300, and the actual force we are going to keep it as 0. Now we need to find out the first. Let us verify our previous problem, right? So we are going to take epsilon C is 0.0035, and then I'm able to achieve the force equilibrium corresponding to a depth of 130.1 millimeter. And then here, as you can see, I'm able to balance the tensile force and the total compressive force consisting of the equivalent compressive force in the concrete and the compression force in the reinforcement. So we're able to achieve the balance. Then the corresponding moment capacity is 92.5, and the curvature is 3.84. So 92.5 and 3.84, we're able to validate our Excel sheet using the based on the theoretical using the formulas that we have calculated. Now we are going to change epsilon C to 0.0035, right? And then in order to achieve equilibrium of the cross section, do we need to increase or decrease the value of neutral axis, the depth of neutral axis? So here CC is 970, CC plus CS, and TS is 628. Yeah, so we need to decrease the value. Okay. Okay, we're going to decrease it further. Okay, 90, 85. Okay, 83, We need to increase it now, 84. Okay, we need to reduce it slightly, 83.8, 83.9. Okay, I think we can stop here. Like we can take the value of x as 83.9. X is and correspondingly, okay, taking the moment about this section, about the tensile reinforcement, okay, we have the value of ms 225.6 and 41.7. So option C is the correct response. So we'll plot and compare the moment curvature graphs for singly reinforced and doubly reinforced beam given in question 1 and question 80, right? So we see that, so here for the singly reinforced, have the doubly reinforced, right? Oh, sorry. 1256.64 mm square, 1256.64 mm square, and 600 mm square. So here we can see that uh, actually using the area of compression reinforcement of 600 mm square in addition to the tension reinforcement helps us increase the moment capacity marginally, but more importantly, as we were discussing earlier, it helps in improving the ultimate curvature, which is very important to ensure the ductile behavior. Okay, so here we can start to see the benefits of using the doubly reinforced cross section. Now, to conclude the class, we have a very interesting problem. Okay, now we will see what will happen when the beam is reinforced with 2% reinforced on the tension side, and the area of the compression reinforcement is 2%. Okay, so AST is equal to 4% and ASC is 2%. So what would be the corresponding AST and ASC? Like, can you please calculate? So 4% is 0.04 into 250 into 450, right? So that will give a value of 4500 mm square, and this is 2250 mm square. Okay, so we need to find out the moment of resistance and the curvature. Let us go to the Excel sheet. The width and depth are the same. This is 4500, so that is 4% reinforcement. This is 2250, that is 2% reinforcement. Then the remaining properties are the same, and epsilon c is 0.0035. Okay, now in order to achieve the balance, we need to increase the value of x, right? Let us try 100. We'll increase it further, 150. Increase it even further, 160. Increase it even more, 170. 175. Okay, increase it even more, 180. 190. 200. Okay, 205. We need to increase it slightly more. Okay, 205.8. Yeah, I think we can stop here. And we can see that for x is equal to 205.8, x is equal to 205.8, we are able to achieve the force equilibrium, that is Cc plus Cs is equal to Ts. And correspondingly, we have the moment capacity as 740 and 17.06. 740 and so option D is the correct response. So now we'll plot and compare the graph for doubly reinforced and singly reinforced. For the doubly reinforced, it is, let us AST is 4500 mm square. Now for the doubly reinforced section, we have AST is 4500 mm square and AAC is 2250 mm square. So we can see here the benefits of using a doubly reinforced cross section. So when we use a doubly reinforced cross section, it helps in not only increasing the moment capacity, but also the curvature is significantly increased. Okay, so which is why, even in the practical reinforced concrete structures, we try to provide a doubly reinforced cross section, because not only the forces are reversible, because of the enormous benefits that we receive when we enormous benefits that we receive in terms of the moment capacity as well as the curvature. Okay, so I think with that we have come to the conclusion of today's session. I thank the participants, for their patience and for being throughout the session. So we will meet again for the 7th week of the live interaction session. So if there is any doubts or any feedback from this session, please let me know.
Sir, what for any doubly reinforcement,
Yeah.
if compression still is over reinforced, means not yielded, and
Okay.
tension reinforcement already yielded, then this component is which type of failure? It is compression zone failure or tension failure? If compression still is not yielded,
Okay.
means compression still is over reinforced
Okay. You
and
mean to say that?
tension.
Okay. So I would like to, clarify in this way. So first, what we will do is, yeah. So first, what we will do is we will find out the moment capacity. We have the moment capacity. We'll design it as a singly reinforced beam. Okay. But let's say that the singly reinforced capacity is 600 kilonewton meter. Okay. And you have already provided 4%, which is the maximum permissible reinforcement. But let us say that the actual demand is 800 kilonewton meter. Okay. So the demand is 800. So at that point, we are going to provide a doubly reinforced. So in the doubly reinforced, what we do is, like we are having the, in order to accommodate this extra 800 kilonewton meter, we are going to provide the ASC. I'm sorry, ASC. So here AST1 corresponds to the singly reinforced cross section, and here AST2 will accommodate for this additional moment, which is coming from the ASC. Okay, so we will always make sure that, when we are providing that this CC plus CS is equal to PS. Okay, so what I'm trying to say is that we will always make sure that it is failing in the tension only. Okay, so I hope I'm able to make it clear.
Okay, no problem.
Yeah,
But what if what if compression steel is over reinforced? Then what the section is going in which failure? Tension failure, compression failure?
so if it is over reinforced, actually, okay. If you're asking that you're providing too much of compressive steel, right?
Yes, yes, sir. Yes, sir. Yes, sir.
Okay. So if you're still providing compressive steel, like it is strong in compression, right?
Yes.
So it'll undergo tension failure because the
Okay.
compressive it is still able to resist the compressive forces, but it is still weak in tension, right? So that is why it is going to fail in the tension only. So it's a ductile failure.
Okay. Okay, sir.
Yeah,
Thank you, sir.
yeah. So, yeah, thanks for joining, and we'll meet again. And if there is any doubts,
Okay, sir.
feel free to
Sir,
post in
sir.
the, yeah.
Uh, for assignment week number 4, there is a lots of problem for my calculation. Actually,
Okay,
the tension capacity all I have calculated is wrong, but
okay,
compression capacity is good. But
okay,
tension capacity not match with that whatever given in the result. But
okay.
you today
So,
you write that NPTEL is provided. That's why
yes,
I'm waiting.
so we are actually working with the NPTEL team that, so I hope you can see my screen, right? Hello?
Yes, yes, sir.
So
Yes, sir.
basically, what we will do is like presently we have this weekly sessions. Sorry, the weekly recordings are there.
Yeah.
In addition to that, after this assignment section, so we are planning to provide a detailed feedback in this actually portion. So we are working with the NPTEL team, and we are going to make sure that we are going to get the detailed solution as soon as possible. So
Okay, sir.
then
We
you
will wait.
can actually look at where you're not able to, why the answers are not matching. Then if there is any doubt, like please feel free to post it in the discussion group, or you can mail it to me also, and I'll try to solve it on paper, and I'll share the solution. Okay, but
May I know
please,
your
okay, so you can please wait for the detailed solution. I am
okay.
sending the link of my website, so there you can find my email address. Okay, I'm going to post it in the chat box. So here you can contact me. My institute email ID is there, and my personal email ID is there. You can reach out to me in either of them. Okay. Yeah, you may please feel free to contact in case of any doubt. Okay, I think with that we can conclude today's session.
Okay, sir. Thank
Yeah,
you,
yeah.
sir.
Thank you for joining. Look forward to meeting you again next week.